Hi, my name is Michael Howard, and I'm here to present OD32, Designing Secure Azure SQL Database Solutions. This is a pretty fun presentation. We go through pretty quickly through a whole bunch of security capabilities that we have in Azure SQL Database. I'm also the co-author of a book that came out last year, end of last year, called Designing and Developing Secure Azure Solutions. And a lot of what we talk about in this session, we go into much greater detail in the book. So the main objectives of this, I was going to put an agenda here, but it's not really an agenda. It's really just a bunch of objectives that I sort of want to achieve. The first one is just some basic elements of secure design. Like, what does it mean when you're thinking about designing a secure system? And secondly is how to correctly choose some of those mitigations and some of those technologies that we have in Azure SQL Database to help build more secure solutions. Before we get sort of stuck into this, I really want to make an important point, and that is you've got to really understand what mitigations are provided by various security technologies. If you want to use A or B or C, whatever they happen to be, what do they actually mitigate? Like, what do they really fix? Because sometimes you may actually not use the right mitigation. And so hopefully this will help clear up a lot of the differences between the various mitigations that you have at your disposal within our database products. So before we get stuck into that, let's take a little step back and let's actually add some structure to all of this. Like, how do we think about security when we're designing a system? This is actually lifted straight from the book. As you can see, it's probably chapter 13. And when you're thinking about, what mitigations we're going to use, what security technologies we're going to use, you really have to think about, one, what security property do they provide, and at what plane, right? So there are two planes, right? There's the control plane, the data plane. The control plane is the management plane, right? It's how do you manage these systems? And then data plane is essentially the mitigations that come into play for your users using the system. Then you have all these different things you need to think about, like authentication and authorization and audit, and then the various types of cryptographic controls. There's another session called OD31. I actually go into more detail into the three sets of cryptographic controls, and then finally network isolation. So on the next slide, if we look at sort of the security features that are provided by the various Azure SQL Database products, or SQL Database products for that matter, you'll see we've got things like for authentication, for server authentication, we have TLS. For client authentication, you can actually use Azure Active Directory, or you can use SQL Login. I'm not going to go into all of these in any detail because we're going to explain some of the key ones as we move forward. But as you can see, there's actually a whole bunch of security technologies that you have at your disposal. And here's some more as well, right? So cryptography on the wire, cryptography in use, and then finally network isolation. Again, it's really important to understand which mitigation, which security technology comes into play at which plane, control plane or data plane, and also what it's actually trying to solve. So let's go and look at the very first one of my favorites, which is TLS, alongside all my other favorites. So TLS, or Transport Layer Security, what was often referred to as SSL back in the day. By the way, TLS is essentially an IETF ratified version of SSL. That's really all it is. SSL was originally invented by Mozilla, and then finally the Internet Engineering Task Force took it over, and it became TLS. What the single most important feature that TLS actually offers, which actually surprises a lot of people, is server authentication. If you ask anybody, like, what does TLS actually do? They'll often say, oh, well, it protects my credit card on the wire, which is true. But you have to have the server authentication first. You can't have a secured channel until you know who you're talking to. And that is the most important security feature that TLS provides, is server authentication. After you have that server authentication done, that's when you can have a secure channel. You can use encryption, and you can use tamper detection controls like HMAX. And a correct TLS configuration is absolutely critical, like no self-signed certificates. If you have a self-signed certificate, that's telling me that you're not authenticating the server. You're really not. The best analogy, and I'm not a fan of analogies, but the best analogy is a little bit like, say, flying to South Korea and writing your own passport on the plane. I don't think the South Korean border guards are going to let you into the country somehow just because you wrote your own certificate, so your own passport. And it's the same with self-signed certificates. Please just don't use self-signed certificates. people think, oh, I use self-signed certificates in dev and then I use normal certificates in prod. No, just use real certificates in dev as well. Even if that means setting up your own certificate authority, which is a whole nother discussion. But please don't use self-signed certificates. Azure SQL Database and SQL Server prior to 2019 support TLS 1.2 and below. Azure SQL Server 2022 also supports TLS 1.3, but you must configure it. And this is one of the great examples of one of the benefits of using PaaS solutions over IaaS. So, for example, PaaS is platform as a service, say running Azure SQL Database, versus IaaS, say running a SQL Server inside of a virtual machine, or on-prem for that matter. You have to configure the TLS. Whereas in the case of PaaS, platform as a service, so Azure SQL Database and Azure SQL MI, we take care of handling the certificates for you. So when we're looking at connecting to a SQL database, we have to use a connection string, right? We're all very familiar with ODBC, connection strings. There's two major settings you need to worry about. The first one is encrypt equals true and trust server certificate. If I had my way, I would rename the encrypt option, but it's been around for a long time, so it's not going to happen because it's more than encryption. It really, in my opinion, it should be like channel protect, right? Because that's precisely what it does. It's encryption and tamper detection. And then finally, trust server certificate. This is a really important one. If you have trust server certificate equals true, that means I actually don't care what I connect to. There's no authentication going on. It's basically whatever you present to me, server, whatever the server presents to your application, you're going to trust it. And that basically means you do not know who you're talking to. You just don't. Trust server certificate equals false doesn't mean don't do any certificate validation or anything like that. It means I don't trust it by default, so you must do the certificate validation, right? So chaining up to a trusted root, things like date range checks, key validation, like is it a server authentication certificate? Things like, has it been revoked? There's all these other things that you need to worry about, right? So the recommended settings are encrypt equals true and trust server certificate equals false. Now, the really good news in SQL Server 2022 is that we now have an option for even tighter TLS policies where you can do encrypt equals strict. And essentially what that does is it disables trust server certificate altogether, and it will do the correct certificate checks. It also allows support for TLS 1.3. And essentially what we've done in SQL Server 2022, and this is actually quite a lot of work, is we've broken apart tabular data stream, TDS, which is the native SQL on-the-wire protocol, and TLS 1.3. We've actually broken them apart, and so that we can actually upgrade one over the other. Historically, TDS and TLS were kind of intermingled, but that has now been broken apart. So this is fantastic. If you're using SQL Server 2022, you can actually now use TLS 1.3, so long as you're running it on an operating system that supports TLS 1.3 as well, which is primarily Windows Server 2022, primarily. Okay, so that's server authentication out of the way. So basically TLS, and do TLS correctly. For client authentication, you really have a bunch of options, but the big one that we really are big fans of, and the SQL team is really pushing heavily, is to use Azure Active Directory. This is always the preferred way of doing client authentication. And the reason for this is because Azure Active Directory is handling the credential and not the application and not SQL Server. If you use SQL authentication, there is a password verifier, not the password, a password verifier stored in SQL, which means that if SQL is compromised and the attacker has enough privilege and can get that data, they have something that will help them try to derive the password. I'm not saying they'll be successful, and it is actually a lot of work, but it's still there, right? But in the case of Azure Active Directory, the credential is not there, period. It is not there. And so if the attacker does actually compromise the system, the attacker doesn't get the credentials of the users. This is really important when you're looking at zero trust, especially assume breach, because assume breach assumes that you've completely compromised the environment. Does the attacker get something critical like the password or a password verifier? And the answer is no, because it's not there. For non-user accounts, so for example, I don't know, what's a good example? Say a virtual machine or an Azure Function app, you can actually use a managed identity. And a managed identity, again, is an identity that's handled by Azure Active Directory. And so when the VM starts up, as an example, and tries to make a connection to SQL Server, it will actually connect as the managed identity on the VM. And again, the credential is not there. I was working with a healthcare organization, it was a long time ago, and they had a specialized application running inside of a VM, and they had to store the SQL credentials in the VM. The problem with that is if the VM is compromised, the attacker now has the credentials to get into the SQL database. So we ended up making a change so that rather than doing that, we actually made the connection as the identity on the VM instead. And again, if there's a compromise, there's no credential there because it's all handled by Azure Active Directory. Again, absolutely fantastic when you're thinking about zero trust and assume breach. Here's another example. If you turn on Azure SQL auditing, you've really got a couple of options if you're using a storage account to store the audit logs. But how do you make sure that the SQL instance can actually write to that storage account? And you have two options. The first one is to use a managed identity, which means that Azure SQL Database will have its own identity, and then you can restrict access to that particular SQL instance to that storage account. The other option is to use a storage access key, a SAS key or a SAS token. The problem with that, when I'm reviewing a threat model, one of the first questions I ask is, where is that storage access key stored? Because you need to protect it. Well, people say, well, it's stored in Key Vault. Well, how do you protect that? Well, we have an RBAC control on it. Well, how do you identify the SQL instance that's connecting? And it's like turtles all the way down, right? So managed identities, the reason why you would use a managed identity here is because that way SQL is not storing a credential somewhere. And this is always the best way of protecting things like this, is to use managed identities. So let's have a quick look at our environment so far and kind of what it looks like. You'll see on the left-hand side, we have the client's authentication using Azure Active Directory. Perfect. All communication absolutely everywhere is using TLS. Perfect, because that's giving us server authentication and it's giving us channel protections as well. In the middle there, we've got SQL itself. If you connect to SQL Server, that's authenticated using TLS. And it's using a managed identity when it acts as a client writing out to the storage account for its audit logs. This looks like a really fantastic example. And we're using a restricted RBAC policy on the storage account to restrict access just to that particular SQL instance. This looks really, really good so far. Now let's look at authorization. And again, you've got to really understand here, you've got control plane authorization and you've got data plane authorization, and they're different. So the control plane, this is all Azure, right? So if you're deploying an Azure SQL Database or SQL MI, you will assign people the appropriate roles to do SQL administration. So for example, SQL Database contributor there can create new instances of database instances, but they can't look at data. They can't manipulate security policies. They can't add users to the database, right? Then you got SQL Security Manager, which is kind of the opposite. They can do security policies and so on, but they can't spin up, say, a new database instance, and they certainly can't look at the data. So this is two examples of different roles, control plane roles, that are opposite ends of the spectrum, right? You don't want to grant someone both these roles at the same time. So these are examples of control plane, a couple of control plane roles. SQL itself also has roles, right? And it also has permissions as well. And it also has control plane roles and data plane roles. It's kind of weird in that way, but that's just a legacy of on-prem, right? Where you could have control plane roles and data plane roles. I'm not going to go into all the details here, but there's, you can go and look at learn.microsoft.com, and there's plenty of documentation around the various server roles and database level roles. One of my colleagues has written a blog post and trying to break some of these permissions up. His name is Andreas Walter. I would definitely urge you to go and look at that, where he tries to take out some of these roles and make them much smaller, much more granular. So that way you could grant someone just a very, very small role as opposed to like a big role that gives people a whole bunch of access to a whole bunch of things. And that's an ongoing work as well. So hat tip to Andreas there. Next, we come on to one of my favorite topics to go with all the other favorite topics, and that is cryptographic controls at rest. And we have a whole bunch that we have at our disposal here. I really want to stress something that to me is really important, and that is that you may have heard this whole notion that security is only as strong as the weakest link. It's actually not true. Cryptographic controls are a massively beneficial last line of defense. Like when everything else has just been absolutely blown away and destroyed, and the attacker is in the environment, a well-designed and correctly designed cryptographic control can actually mitigate those threats. So for example, let's say you blow the firewall away, you some weak RBAC policies, blah, 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 right? And the attacker gets the data, but it's encrypted and they can't get the key. Okay. I mean, not great, but at least it's not plain text, right? When the attacker has all the data and has all the social security numbers and has, everyone's prescription information or, healthcare information. Much better that the data is encrypted. And that's often why security mitigations are often referred to as compensating controls. They're there to compensate for other weaknesses in the system. And cryptographic controls, in my humble opinion, are actually one of the best sort of compensating controls because they can really, really help out, if a whole system has been utterly destroyed. So the first of the controls, I think everyone kind of knows this by now, is transparent data encryption. It's been around for a long time. The nice thing about it is it's really easy to use. There are zero code changes required. It just works. Remember, I said very early on, it's important to understand what the control actually mitigates. In this example, TDE is designed to mitigate the disclosure of sensitive data from a stolen data volume, right? So if someone walks into a data center, steals the volume and walks out, or if you've got on-prem and someone walks in and, you've got a server under the desk and gets hold of the hard drive and walks out of the environment, that they can't decrypt the data. It's still useful, incredibly useful, but probably the most important part is actually backups, because backups are actually encrypted using the same key hierarchy. And backups are completely away from the server. It's not uncommon to say store a backup every once in a while on-prem, right? Or in a storage account or something. But the point is that is away from the SQL instance itself. And transparent data encryption is really useful in this environment. The root key, there's a whole key hierarchy, which I'm not going to go into, really should be held in Key Vault. That includes SQL Server in a VM. And then you'll provide access control using, say, a managed identity to access the root key and then decrypt, or the hierarchy of keys that are then used to provide the encryption and decryption of the data at rest. There's a newer technology called Always Encrypted. It's relatively new in the overall scheme of things. And in OD31, I actually go into this in much more detail. So when you think about Always Encrypted, you've really got this sort of spectrum, right? So on one end, you've got databases which are designed to be queried. I mean, they're designed to insert and delete and update and so on, but they're really designed to be queried as well. And then at the other end, you've got encryption, which is designed to do the exact opposite, right? It's designed to stop you looking at the data. So we've got this real problem here. We've got these products that are designed to be queried, and then these features that are designed to stop you from querying. What's interesting here is that Always Encrypted is kind of in the middle. It actually, and this is a really important point here, Always Encrypted, I'm going to read it verbatim because I'm very, very specific. I've always been very specific about my words. Always Encrypted allows you to perform some queries over encrypted data, without decrypting it at the server, Stop and think about that for a minute. What it means is the data is encrypted at the server and is not decrypted at the server, which means that the plain text is not in the server's memory at all. In the main process memory, it's not. And the way it works is basically by doing queries over ciphertext is essentially what it does. There are two types of Always Encrypted. There's Always Encrypted with secure enclaves and Always Encrypted without secure enclaves. Cosmos DB also supports Always Encrypted, and it's the non-enclave version. What's really important here is that in both versions, whether it's the enclave or the non-enclave version, the encryption and decryption keys are not in the server process memory. They're not there at all. All the encryption and decryption, for the most part, is done at the client. In the secure enclaves, there's a variant to that, which I'll talk about in a minute. But essentially, the full encryption and decryption is done at the client. So the ciphertext going back to the client. Then the client driver decrypts the data. And again, I go into this in more detail, much more detail in OD31. If the server is compromised, there's no plain text there. There's if you've got a column encrypted with Always Encrypted, the plain text isn't there. And there's no key there. It's not there. So again, this is really important when we're talking about assumed breach and when we're talking about zero trust. Incredibly important because the data is just not there. So there's nothing for the attacker to actually benefit from at all. Now with the enclaves, there's two versions. Sorry about that. So there's two versions. The first one is SGX, which stands for Software Guard Extensions, which is a special set of instructions and functionality on some Intel CPUs. And there's also VBS enclaves, which stands for virtualization-based security enclaves. So in the case of VBS enclaves, it uses the Azure hypervisor. So the same technology that we use in Windows and in Azure, for that matter, to isolate one VM from another. It's the same technology. But what we're doing, instead of actually isolating part of the query engine, is being isolated in its own little host somewhere off to the side somewhere. So even if you compromise like the SQL Server, it actually can't get to the memory region because it doesn't exist, because the hypervisor is actually limiting access to that enclave. And in the case of SGX, the actual isolation is all the way down to the CPU. So the SGX does provide stronger isolation and stricter isolation, but it does require specific hardware under the hood. So when you're deploying an Azure SQL database, you would need to configure it. What's cool about VBS is it has much more compute options and much more region options as well compared to SGX. And it's frankly a lot easier to configure than SGX enclaves. Now, with Always Encrypted, it will require code changes. It's just as simple as that. If you've got an existing system and you want to use Always Encrypted, you will need to change the code. That being said, if you're building a new application, you should really consider using Always Encrypted for those sensitive columns. It's much easier to design a system from the get-go, understanding how Always Encrypted works. Again, remember, the SQL Server process does not have the keys. They're not there. Now, in the case of the enclave versions, the key is actually in the enclave. It's pulled out of Key Vault and so on and so forth, and unwrapped in the enclave. But the actual encryption and decryption is done in the enclave as well. So if it needs to do a query, it can decrypt the data in the enclave, but it still returns the ciphertext back to the customer. So that's the only time it's actually exposed. Again, but it's not exposed to the attackers. It's not in the same process as SQL Server. So going back to our environment again, you see we've got all the stuff that we had before, but in the top right-hand corner, we've added Always Encrypted. And so we can have Always Encrypted columns. So for example, healthcare information, social security numbers, anything that's considered either private healthcare information or personally identifiable information, you can always, can encrypt with Always Encrypted. There's also SQL RBAC, permissions and roles that you can apply from an authorization perspective, and also row-level security if you really wanted to. And I haven't talked about row-level security at all. That's a whole nother discussion unto itself. And other than that, nothing else changes. Always Encrypted, for the most part, is about disclosure of data, right? It's reducing or limiting the potential impact for disclosed data, but it doesn't really address sort of bulk data integrity, and that's where other technologies come into play that are available in SQL. So, as I mentioned, if you got Always Encrypted, so I talked about this in a bit more detail in OD31, but you can actually take a cell in Always Encrypted and actually paste it into another cell. The integrity detection is actually at the cell level. It's not at the row level. That can be important for some people. If a user has enough access, they may be able to do that. May be able to pull off that attack. Maybe. So, but what about sort of bulk tampering in general, like changing transactions? Right? There's a demo that we gave, like a World Cup scenario where you're where you're betting on a team winning. So, for example, you may have, say, the Netherlands versus Belgium, right? And you say, okay, Belgium's going to win 2-1. Well, what happens if the Netherlands actually wins 2-1, and you have a malicious insider where you phone your malicious insider up and say, hey, change my bet from Belgium winning to the Netherlands winning? And so the malicious insider changes it, and you end up earning $10,000, and you split it 50-50 with the person on the inside. That's actually a real threat scenario. It really is. I mean, not just, betting on the World Cup, but just in general. So in this case, the malicious insider has full access to everything. So how do you mitigate that? And so we have a technology built into Azure SQL Database and SQL Server 2022, and it's also now in preview in SQL MI, and that is a technology called Ledger. This builds on top of temporal tables, and essentially what it does is on a time-by-time basis, on a short period of time, it takes the data and it hashes that data, and it uses SHA-256 as the hash, and then stores those hashes into a protected storage account. This next part is critically important. So the actual data structure is called a Merkle tree. Doesn't matter what it is. It's just a hierarchy of hashes. That's all it is. And the reason why we do that is just for performance. But it's critically important that you store that Merkle tree on tamper-proof service, and you really have two options: storage account with the immutability bit flipped, so it's immutable storage, or Azure Confidential Ledger. You can use either, and they have essentially they are tamper-proof, right? There's not like, it's hard to change. It's like you can't do it. This is much better than an RBAC control, right? So if you have an RBAC control, an inside admin can probably override that RBAC control and make the changes. In this example, if they do it, then the Merkle trees are invalid, and we can actually show that, hey, this change was made, and we can see that, there was tampering made to the actual transaction. So I really can't stress this enough. You've got to store the resulting data structures, which are all automatic from SQL Server or Azure SQL Database, and actually store them either in immutable storage or in Azure Confidential Ledger. So now let's go back to our scenario again. And you see here, it's still the same. We've still got always encrypted up there and everything else that we have. We've added two options down, or three things down the bottom. The first is the actual ledger itself, which is just a set of special tables. And we can put RBAC policy on that and use immutability as well, right? So a confidential ledger or a storage account with the immutability bit flipped. And there's also auditors. You can have a separate role that just does auditing to make sure that, hey, the audit logs look good. And that's a special role that's also built into the product as well. So I want to sort of segue really quickly into threat modeling, and you'll see why I'm doing this in a moment. So at Microsoft, we're big believers in threat modeling. I review threat models at least probably 3 or 4 minimum a week. And what we're looking at is looking at the design of a system. And the way we look at it is through this lens, through a thing called STRIDE, which is essentially what can an attacker do. So for example, I have a process, say a SQL Server process. It's subject to spoofing. Like, how do you know it's actually the correct SQL Server process and not something else? And that's spoofing. And then you mitigate spoofing with certain techniques. Then there's tampering, be able to change data. Repudiation is reneging on a transaction, which is actually the ledger scenario. A lot of repudiation threats start life as tampering threats. Information disclosure, denial of service, and elevation of privilege. What's interesting about all of these is they're mitigated with these broad techniques. So for example, spoofing, you mitigate with authentication. And there's a whole bunch of different technologies that you can choose. Believe it or not, we've actually talked about some of these technologies. And in fact, if I look at the diagram that we brought up before, and I sort of overlay the STRIDE categories, you'll see, like, for example, when a user connects to SQL Server, how do we know it's a valid user? That's a spoofing threat. And you mitigate it with authentication. In this case, we're going to use AAD. Perfect. When the client connects to the SQL Server, how does it know it's actually the valid SQL Server? That's a spoofing threat, and we mitigate that with TLS. Fantastic. That's a great mitigation. Data on the wire is subject to tampering and information disclosure. We actually mitigate that with TLS. So we've got a twofer there, right? We actually mitigated two sets of vulnerabilities, or two types of threat, with one technology, which is TLS in this case. If you look down the bottom, you'll see that we've got the ledger storage, and you'll see that we've got things like tampering and repudiation. The T and the R, they're mitigated by using ledger. And you can see all the way through this, you've got various mitigations that come into play to mitigate those specific threats, which are the STRIDE categories. One thing that's not in here is denial of service. And you may say, okay, I'm going to just rely on the built-in Azure mitigations around denial of service, but you can also opt in for DDoS protections as well if you want. But right now, there's nothing in here that talks directly to sort of network level DDoS. So this is, believe it or not, this is actually the start of a threat model. Where we're looking at the system from a sort of design perspective and making sure that we have all the appropriate mitigations in place. So I hope that makes a bit of sense. So some things for you to look at as you're designing systems. I really want to stress here that the big focus from the Azure security team, the Azure database security team, is always encrypted, ledger, and Azure Active Directory for client authentication. You could argue TLS as well for server authentication, but that's kind of just there. And mainly because you have so many options for client authentication. That's why we really want to push AAD authentication, because that way there's no credential being stored. It's really important you understand some of these core security principles, right? The spoofing. Well, how do you mitigate that with authentication? Well, what's the correct technology to choose? And do understand how specific technologies actually mitigate specific threats. And is it the correct technology to use in that specific scenario? Learn threat modeling. If it's something that's, something you're not aware of, you really should learn it. Learn the basics of it. You can go to microsoft.com/SDL, which stands for Security Development Lifecycle. There's lots of documentation up there about threat modeling. Big fan of threat modeling. And then finally, apply these security skills to your own designs, right? So as you're designing something, think about, okay, I've got a process here. How do I authenticate that? I use TLS. Fantastic, correct answer. I've got the data at rest. What's the RBAC policy? Is the data encrypted? If so, where are the keys stored? These are sort of questions that you're going to be asking yourself as you move through, design of an environment. And frankly, so I've got to push this as well, but go ahead and pick up a copy of the book, Designing and Developing Secure Azure Solutions, because you go through all of this in gory detail, including threat modeling, including cryptographic controls, and there's a big section, chapter 13 on database controls. So with that, I'm done. I hope you found this useful, and thanks so much for tuning in.